Hi everyone, welcome to week 7 of distance learning. We are going to be looking at log functions this week. This is a new topic for most of you. The word log is short for logarithm. In this lesson, we're going to be looking at how exponential functions, we have done exponential functions before, we're going to be looking at how an exponential function is related to a logarithmic function. We are going to interpret what a logarithm is. We are going to look at common logarithms. That means that they have a base of 10. We're going to be looking at logarithms that don't have a base of 10. And then we're going to be writing an equation from log form to exponential form. I'm sure all of that sounds like, what the heck did she just say? So let's look at what a logarithm actually is. So we're going to start off by graphing this and relating it to an exponential function. So the picture that you see here where it says graphing activity, it says graph the exponential function f of x is equal to 2 raised to the x. An exponential function is any function that has a letter as the exponent. So here you'll see that 2 raised to the x, the exponent is the letter x, which is a letter, which means that it's an exponential function. And you'll see that it's graphed in that blue curve on the graph below there. Then we graph the logarithmic function. So the log that you see, that means logarithm. The way that you would pronounce this is log base 2 of x. So you'll see that that is graphed in red. And then if you look at the green line that's going through that graph, that green line is y is equal to x, or f of x is equal to x. This is the same thing as saying y, meant for that to be a pen, saying y is equal to x. Remember that if two functions are inverses of each other, they reflect over the line y is equal to x. So that means if I look on both sides of this line, it's going to be a mirror image on both sides of that green line. So some similarities between these functions, we can say that they both have a curve shape. Okay. One of them has the x-intercept at 1, 0, and that would be the log function. So I'm just going to put a little red dash beside it to represent that it's on that curve. The other one has a y-intercept at 0, 1. And that would be the exponential function. So I'm going to put a blue next to that because it's blue on the graph. So they both have a curve shape, but notice that their x and their y intercepts are switched almost. Since they've reflected over that line y is equal to x, that also means that their x and y values are flipped. So it would make sense that the x and the y intercept here are kind of flipped. Okay. So logs and exponentials, the big thing that we want you to get out of that is that they're inverses. So I'm going to write logs and exponentials, just going to abbreviate, are inverses. That means that they undo each other, and it means that they're reflected over that line y is equal to x, and it means that their x and their y values, if you were looking at a table, are flipped. Okay. So how are they related with respect to linear function? Y is equal to x. Again, we're going to say they're reflected over that line. Thus, they are inverses. Okay. So I'm going to fill in the table that's down here based off of the points. So the really easy point that we already know, f of x is blue, this one is red. Okay, so I already know I have the point 0, 1, so I can go ahead and fill that in. And then on the other table, I have the point 1, 0, so I can fill that in. To fill in the rest of the table, notice the scaling of this graph does not go by 1. So like this point right here, that is not the point 1, 0 because the point 1, 0 is over here. So be careful when you're looking at the scaling of this graph. Instead of using the points on the graph because they're not going to be super accurate, we're just going to fill out the table by hand, and we're going to use some of those exponential laws that you learned, I don't remember which week it was like maybe 2 weeks ago. Those exponential rules that you learned, we're going to use those to fill out the table. So the function f of x, we said that it was equal to 2 raised to the x. So that means that all of these x values, I'm just going to replace them wherever the x is. So if x is equal to -2, that means I'm going to keep the base of 2 the same, and I'm going to replace the x with -2. Okay? Whenever your exponent is a negative number, we always do 1 over base to the positive exponent. So I'm just changing that -2 to a +2. And then this would become 1 over 2 squared, and 2 squared is 4. So the point I get here is -2, +1 over 4. On the next one, I'm going to keep the base of 2 the same, and I'm going to replace the x with -1. So this would become 1 over 2 to the first power. Any number to the first power is itself, so this would just be 1 over 2. So this point would be -2, +1/2. The next one, we already said that that was equal to 1, so this point would be 0, 1. Okay. Next one, the base of 2 stays the same, and the exponent gets replaced with 1. I don't have to do any flipping here of a fraction because the exponent is not a negative number. You only flip it if the exponent is negative. Since the exponent is positive, I can just evaluate that. So 2 to the first power is just 2. So this point would be 1, 2. Last, I'm going to replace the exponent with a 2. 2 squared is 4. So this point would be 2, 4. Again, all I did to get those numbers was I just replaced the x that's up in the exponent with whatever x value was on my table, and that's how I got the points that are listed there. Now, let's do g of x. So g of x, if you look at your graph up here, we said that it was equal to log base 2 of x. Okay? So I am not going to evaluate these quite yet. I'm just going to rewrite it in log form by replacing the x that's here with whatever x value is on my table. So this would be log base 2 of 1 over 4. This would be log base 2 of 1/2. Log base 2 of 0. This one had already told me it was 0. And then I've got log base 2 of 2. Okay, so the points that would be generated, I would have 1 over 4 and log base 2 of 1 over 4. I'm going to pause the video and write this so you don't have to sit through me painfully writing all these out. Okay, so that is our table. Now let's take a look at the domain and the range for our blue function, which is the exponential function. So looking back at your graph, at the blue graph here, my domain, pretend that this graph has got arrows on both ends of it. It's going to keep going on forever in both directions. My domain, if it goes on forever in both directions, is always -infinity to +infinity. The range here, however, is going to be different because this graph has something special on it. We have talked about that special thing before. It has what's called an asymptote. So right here, when your y value is 0, so along that yellow dotted line I just drew, that is when all of the y values are equal to 0. Your blue curve is never going to go below that line, and it's never going to touch that line. It's going to get super, super close to it, but it's never actually going to touch it. So the way that I'm going to write the range, since that line has a y value of 0, I'm going to go parenthesis 0. The reason I put a parenthesis there is because I'm not actually going to ever be at the value of 0. If I was going to be at the value of 0, that line would be solid and I would put a bracket. Since I'm not actually going to touch that line and the line is dotted, I'm going to put a parenthesis. So I'm going to go from 0 to infinity. okay? This says that I can, for my domain, I can plug any number into the function and I can get a negative number or a positive number out. The range says that I can get any answer that is really, really close to 0, but not quite 0, and any positive number that's larger than 0 I can get out of 2 raised to the x, okay? For your HK, I'm just going to write this is like your general exponential equation here. So my HK, I don't have anything, if I'm looking at 2 raised to the x, I don't have anything attached to the x, so that means that my h value would be 0. And then I don't have anything that I'm adding on after it, so my k value is also going to be 0. Just to kind of show you an example outside of that, let's pretend I did like, I don't know, 2 to the x minus 1 plus 4. In this case, my h value would be positive 1 because remember x lies, so it's always the opposite sign, and my k value would be 4. But since we have 2 raised to the x, there's nothing attached to the x and there's nothing in the back of it, so your h would be 0 and your k is also going to be 0. Okay. Your asymptote here, is it vertical or horizontal? Well, that yellow line, y equals 0, that's a horizontal line. Horizontal goes side to side. So my asymptote, I'm going to circle horizontal. And then the equation of our asymptote, we said it was at y is equal to 0. Okay, moving over to our red function, the log function. So domain and range, let's take a look at our graph here. This graph is going to go on forever in both directions. But something kind of tricky about the log graph. Notice that, remember that your domain looks at x values. Notice that all of the x values are all on the positive side of the x-axis. We don't have any x values that are going to be on the negative side of the x-axis. So I don't have, past this kind of line here, I don't have any numbers, any negative x values that are going to be listed for a log function. So that means that our domain is going to go from 0 to infinity, okay? That's kind of also telling me where my asymptote is for this function. So instead of my asymptote being at y equals 0, now I've got this vertical line, it's at x equals 0. So I'm going to go here to my asymptote. We just said that it was vertical, and we said my equation was x equals 0, okay? So my domain, I can't touch 0. I can get close to it, but I can't quite touch it. So it's going to go 0 to infinity. And then our range, looking back at our graph, I can get any positive y value and I can get any negative y value because I've got parts of the curve that are going positive y, and then I've got parts of the curve that are going negative y. So that means that I can get a negative or a positive number out of this graph. So I'm going to go from negative infinity to positive infinity. It's an ugly infinity sign. Okay, so what this says is that I cannot take the log of a negative number because any input, any value that I replace x with, it can't be smaller than 0 and it can't be the number 0. So I can go from 0 to infinity. And then my range, this says that I can get any number out of a log. It can be a negative number, it can be a positive number, okay? For my HK, this function is log base 2 of x. So your general equation looks like this. I don't have anything here, and I don't have anything here. So my HK, again, is going to be 0, 0. So all of the things that are on this page are really core to the topic of logarithms. on the next page, let's really investigate what a logarithm is. So the definition is the exponent by which another value, the base, must be raised in order to produce that number. So that's probably makes no sense to you right now, but there are three main parts of the log, so let's look at what those are. The base is the number, the little tiny baby number that is next to the word log. The argument is the bigger number that's like on the same level as the word log. And then the exponent is whatever number comes after the equal sign. So what we're going to do now is take it from an exponential form to a log form. So I'm looking at this first table. For example, it says 3 raised to the 4th is equal to 81. Right now, that's an exponential form because it has an exponent on it and it doesn't have the word log in it. I'm going to try to rewrite this so that it's in log form. So the base is whatever number is right here. So this number here, that's your base. So I'm going to start this off by writing log, and the base is 3. Then I need to figure out what goes before and after the equal sign. So a logarithm itself is the exponent required to get to a certain number. So the exponent is always going to go after the equal sign. My exponent in this case is 4, so I'm going to put a 4 right here. The only number that's left is 81, so I'm going to put 81. So I have the exponential form and I have the log form. There I just kind of color-coded everything for you. Let's look at the next one. So on the next one, I'm going to start off again by writing log. The base is the number 2, so I'm going to have log base 2. Remember that a logarithm is the exponent needed to get to a certain number. So the thing that goes after the equal sign is always the exponent. So I'm going to put an x here. And then our last remaining piece is the 16, and that's going to go on the inside. Okay? Our last one on this section focuses on a special kind of logarithm. So I'm going to write this as log. My base here is e. And then I've got, after my equal sign always comes my exponent. So this is going to be equal to x. And then in the blue, we've got the 85. Okay. Log base e is a special type of logarithm, and we call it the natural logarithm. So maybe make a little note down here. Log base e, the way that we write this is ln. And that is for the natural log, okay? So log base e is a special type of logarithm called the natural log. So I'm going to rewrite this as ln, natural log, of 85 is equal to x. This next section is about going backwards. So you just went from exponential form to log form. Now we're going to go from log form to exponential form, okay? So that means I need to have a base, an exponent, an equal sign, and then another number. So the base here on number 1 is going to be, what color to use for base? Red. Is going to be 4. So my base, I'm going to put a 4. My exponent, remember a logarithm is the exponent required to get to a certain number. So my exponent here comes after the equal sign is 5. And then I've got my number, 1024. It's going to go after the equal sign. Okay, let's try another one. So on the next one, my base is 9. The number that comes after the equal sign is the exponent, so that's going to be an x, equals 81. Last one, You'll notice this note here: if a logarithm does not have a base, it is known to equal 10. So it's kind of like the mathematical shorthand way of writing it. There is really a 10 here, but if you don't see it written, just know in your head that there's a 10. So if I rewrote this into exponential form, my base is 10. My exponent always comes after the equal sign is 5. And then the number that it evaluates to is 100,000. The way that I teach my pre-cal kids to do this when you're going from log to exponential form, like we just did, I call it the snail. So I'll do like the one that was log base 9 of 81 equals x. The snail means that you start at the base, you go to the exponent, and then you end at the number that it evaluates to. So when I rewrite this, I start here at the base, which is 9. I work my way around. I get here to the exponent, and then I'm here at the equal sign, and then lastly I've got the 81. So you can use that as a trick to help you remember as well. The next section here, I know that most of you don't have a graphing calculator. You can always go to that announcement I made on Google Classroom and you can find the free link to the Inspire to do this. I'm gonna do the top couple of them with you without a calculator, and then you can do the bottom 3 either with or without a calculator, just for you to practice, okay? So this one, it wants me to evaluate this to give it a number. So if I don't know what something equals, I'm just gonna make it equal x because I'm not really sure what it is. So I'm going to rewrite this into exponential form. Right now it's in log form. So my exponential form, my base is 4. My exponent always comes after the equal sign is x. And then I've got 64. So this is asking me 4 to what power is 64? Well, 4 squared won't work because that would give me 16. But if I do 4 to the 3rd power, that would give me 64. So that means the exponent required to get to 64 is 3. So this logarithm is going to be equal to the number 3. Okay. Next, we've got log base 2 of 256. Again, I'm going to set that equal to x. So if I rewrite this in exponential form, that would be 2 raised to the x is equal to 256. So that's asking 2 to what power is 256? This one's kind of tricky. It would be 8. So 2 to the 8th gives you 256. Obviously, you can use your calculator and you can just do like 2 to the 1st, 2 to the 2nd, 2 to the 3rd, and just keep going until you get to 256. So this logarithm here would be equal to 8. Okay, next one. Log base 5 of 1 over 25. So I'm going to rewrite this with an x and put it in exponential form. So you would have 5 raised to the x is equal to 1 over 25. Whenever you see a fraction like this, I want you to think my exponent is negative, because the only way that you're going to get this fraction is if your exponent is negative. So if I did 5 to the negative 1, that would be the same thing as 1 over 5 to the positive 1, which is 1 over 5. If I did 5 to the negative 2, that would be 1 over 5 to the positive 2. 5 squared is 25, okay? So this was the answer that we were looking for. So the exponent required to get there was negative 2. So this logarithm is going to be equal to negative 2. Just while I'm here, I want to look at the log base 6 of 6 that's underneath of it. Again, I'm going to set that equal to x. So this is saying 6 raised to the x is equal to 6. So the base 6 is here, and then the 1 after the equal sign is here. So 6 to what power is 6? Well, I'm trying to get the 2 to match. Any number to the first power is itself. So this logarithm here would evaluate to 1. The other two, the log base 3 of 1 over 81 and the log base 9 of 1, I want y'all to try to do those on your own. My hints here are that any number to the 0 power is 1. And if you see a fraction, I want you to think about a negative exponent, okay? So try these two as practice, and you can always look at the key that's on Google Classroom to see if you got them right. If you have any questions, please ask your teacher. Thanks for watching. Have a great week.